Good afternoon. Buddhikai Tushant. Tushanto Tushantan Buddha. So only you two are here. Another. Hello. Lamaya another. Hello. Ah. Okay. පුතාලා මේ මොකද ළමයි නැත්තේ අද තාම. එක්කෙනයි දැන්. පුතා මොකද කට්ටිය අඩු. Only one person.
Group එකේ නම් share කරා sir message එක.
එහෙමද පුතා?
ඔව් sir.
මේ group එකේ දන්නවනේ අද lecture එක නේද?
ඔව්. mail එකක් දාලානේ තිබ්බේ sir.
ඔව් mail එකක් දාලානේ තිබ්බේ.
ඔව්.
මොකද කරන්නේ අපි?
මම බලන්නම් sir ඊට රෙක්ට කතා කරලා මොකද කරන්න කියලා ඉන්න.
සාමාන්‍ය රූබන්ලා හැම join වෙනවා නේද class එකට?
ඔව් එයාලා පරක් වෙලා හරි join වෙනවා. මම common group එකේ මම share කරේ ආපහු message එක නේ.
ඔව් නේද පුතා?
රෙක්ට ඇවිල්ලත් නෑ තාම team දෙකේම රෙක්ට ඇවිල්ලත් නෑ.
ඔව් නේද? ප්‍රියන්තත් නෑ හසිතලා.
ඔව් ප්‍රියන්තත් නෑ හසිතයියත් නෑ. මම call එක කරන් බලන්න.
අපි මෙහෙම කරමුද? මේ ඊයේ කරපු thermodynamics lesson එක B1 වලට කරපු එක මට එවන්න පුළුවන්. ඒක පුළුවන් හොඳට study කරන්න. හැබැයි promise වෙන්න ඕනේ.
හරි sir.
පුළුවන්ද එහෙම කරගන්න?
ඔව් ඒක
කමන්නේ අපි බලමුකෝ තව චුට්ටක් වෙලා
තව පොඩ්ඩක් කියලා බලමු නේ sir.
බලමුකෝ තාත්තක.
හරි.
තව අපි විනාඩි 10ක් බලමුකෝ B2 එකේ ආවනේ.
හා.
බලමු. 10 minutes බලමුකෝ.
Okay sir.
Okay. Hope your side all are okay. So, again, the gas power cycle understanding, because we have just started only that day. So hopefully today we can do something sizable in the sense we will try to complete at least the concept building part. Okay. So today for this case, we will go with an example. This is a man-made marvelous machine. Yeah. So This is quite big, also very reliable because this used in flying with hundreds and hundreds of people, not one aircraft, thousands of aircrafts daily. So this should be a very reliable machine. And also this should be extremely powerful because just using two of such, okay, carrying hundreds of people and some other payloads. So this is considered, compared to its size, this is very powerful. Okay, so this technology is the behind of this. So this basic technologies, there may be many areas, but gas power cycle understanding is part of this. Of course, understanding gas power cycle is just not enough to produce this. We are talking about producing. Maybe understanding with little bit training of maybe 1 year time, you may be able to service this. You may be able to maintain this. But design, development, manufacturing, okay, or construction, these are quite challenging, okay. But other engineering aspects, okay. But anyway, first of all, we should understand this basic thermodynamics before looking into anything. So you may or you may not be getting a chance to work on this, but this knowledge would be useful in many areas, in many ways. So that's why, so you have long way to go, and the relevancy of this knowledge is to the fullest. So we will see how we can understand this. Okay. Yeah, even for our power generation simple applications, I feel that developing a turbine, manufacturing a turbine probably easier than constructing an engine, because this all single axis. Elemental blades, all blade elements, radially fixed. So this construction may be easier even if you can try this one for power generation and all, maybe compared to engine constructions. So we feel this is little bit, yeah, more advantageous when it comes to development and construction. Okay. So this one I put as gas turbine engine. So engine means this produces mechanical power output initially by using thermal energy. Okay, so that's why even using of the term turbine engine is still common. Okay, so here there are two components. Of course, there are three. There is a compression part, there is an expansion, because expansion produces mechanical work, or turbine part, that is, and also combustion chamber is there to take place the energizing of this working fluid. We will see. Okay, we will see. Yes, air in. Okay, this is quite slow. I put some animation so all became problem. So this is and air out. Okay, air in is something like suction. Okay, air out is something like exhaust or discharge. So air is the working fluid. Yeah. So this is on the ground now, it seems, but high altitudes, this is in the skies. So from the atmosphere, yes, air being received by this with a huge suction power. So air in is not simple, but it is forceful, it's sucking. Because in and out, once continuous in operation, so when it is out, there should be in, because otherwise vacuum is created. So to fill the vacuum, there is a sucking of air in. So these are quite basic imaginations we can understand this. Put some animation, but this looks, yes. This connectivity is wonderful with the surrounding. Air in from the surrounding or atmosphere. Air out to the atmosphere. So there is a connection, which means, so you are letting exhaust go into this and you are receiving, or the turbine is receiving from the atmosphere again. So you can see a connectivity. Yes, that's why. So if you really need to understand this, we need to see this connection. So turbine is not alone flying. It's flying with the help of, yeah, of course, plane is flying, but turbine running with the help of atmosphere. Yeah, so this connectivity is very important. So, of course, not the same exhaust air, but fresh air is taken in from the surrounding. So it's very interesting. So the working fluid wise, there is a connectivity. And heat transfer wise also there is a connectivity, because air in has certain energy level. Let's say same mass but energy level. Low temperature, atmospheric air. Exhaust, high temperature, releasing to the atmosphere. So high energy levels here. So because of this operation, you can see that some energy is dumping, let's say is transferring taken place. We call it, I put it as QR, is the difference between these energies, E out minus E. Okay, so we are discussing the most difficult part here. Okay, so it is quite nice. So this is this thermodynamic cycle of this turbine engine, or let's say turbine, we call turbine engine. Yes, the cycle completes together with the surround. So that's why we call this open cycle, but because open cycle means this cycle connects to surrounding. Okay, so quite interesting really this one. If we further look into this after the suction of air, there is a component here called compression. Let's say the compressor work is W compression. Okay, this sucked air being compressed and transfer for combustion. Okay, that's the power generation strategy when it comes to using of air or gases. You compress it, energize it, then it has more power. Okay, means like condensed power. Okay, compact. So compression is essential. Even in some engines, the turbocharging is there because turbocharging helps for additional compression. A forced full intake, so you can have more thermal energy from combustion to deliver work. Okay. So after combustion, after compression, okay. So here because of the higher compression, when the fuel is injected, because air compressed air, there is no combustion. You have to add fuel. Okay. So adding fuel is taken place at the combustion chamber. Okay, so compressed air at the same pressures and temperatures goes to the chamber. Once the fuel is okay injected or exposed to this compressed air, yes, huge thermal energy is generated. So that's how the energy input to this system. So after that, because of this energizing, there is a huge volume. Okay, volume means not to say huge volume, but there is a potential to become a huge volume when it is changing to the atmospheric pressure. So there is a huge expansion potential there. So this expansion is taken place at the turbine side. So W expansion is much better than W compression. So part of expansion is taken for compression. And finally, expanded, okay? This expanded gas leaves the turbine engine and released to the atmosphere. So this is quite interesting. So this cycle has a connectivity with the surrounding. Okay? Quite interesting. So the very basic, the story type understanding is very important. Okay? So that's about the story. And if we look into the previous slide, this one, so you can see the turbine. Okay, sorry, the compressor, the turbine, and then in between the combustion is taking place. Okay, combustion is taking place. So you can see left side what we have discussed. The right side is a schematic. Ambient can be seen. Okay. This is the compression. Of course, air sucks into the compressor. Compression, high pressure, transferring to combustion chamber, high temperature as well. So with the fuel additions, huge thermal energy generation. So this combustion chamber is a very critical component, same like compressor and turbine, because combustion chamber is where the Q in is taken place for this system. So after that, through the turbine, this gas expands. So the shape says the expansion. Compression reducing, increasing. So W out, that is W in for the compression. So there is a W net out. Okay. So W net out is W expansion minus W compression. Okay. So of course, water exhaust released to the ambient, cold air sucked into the system. So this same mass, same quantities, but different energy levels means somehow we are dumping some energy into this ambient. So the connectivity, same like combustion chamber here on top, you have the ambient here, atmosphere, and you have some Q out. Okay, so that's how this thermodynamic cycle completes. Okay, even we can write energy balances. Okay, we can write energy balances. That is Q in. Okay, Q in minus Q out is W net, energy balance. Quite interesting. Okay, so Q in, Q out, and W net. So we assume no energy losses in between. Okay, so that's a basic assumption with no energy, no other energy losses. So you can have this as well. So based on this, even you can think of some efficiency like thing. Okay, something like efficiency as well. You can think of that. So efficiency in the sense your output is W net, your input is Q in. Okay, so the ratio of this two. Okay, so W net against Q in would be the efficiency for this case. It is quite interesting. Okay, quite interesting. So this is about gas turbine engine cycle. So this cycle, the thermodynamic cycle, is taken place when it comes to energy and work. But in between each and every cycle, the working fluid changes, but its identical. Okay, identical, but it's changing. Okay, so that's how it is. So if you need to plot this cycle, so we will try to plot this. So the gas turbine engine cycle diagram or cycle. So you know the strategy: suction, compression, combustion, power, exhaust. Okay, so it is like that. That's how the cycle is. But we will start from here: the compression, then the combustion, then power, and the connectivity with the surrounding. Okay. But you can do it very nice. Yes, the pressure and volume axis. Okay, we will look into the pressure and volume axis. This is volume. Let's have a quick view. Of course, one pressure, two constant pressure lines. Okay, just for layman understanding, I put this as pressure atmosphere. Okay, but this should be lower than pressure atmosphere because of the suction. But anyway, I just put pressure atmosphere. Okay, no harm. Anyway, that is the low pressure. So you have the high pressure. So this is pressure at the combustion chamber. Okay, pressure at combustion chamber. Okay, good. So air in for compression. So we will look into the compression process first. Compression process. Let's say that is 1. So I'll put this. Compression starts here. So you have big volumes, okay, huge volumes. Let's see. Then this, during compression, pressure goes high and volume becomes less. So it will be like this. Okay, so that may be 0.2. 0.2. Okay, and your volume level may be squeezed. You cannot see it. Then, okay, then there can be energy additions at constant pressure that is taken place at the combustion chamber. So once energy added, volume at 0.2 moves to somewhere else. The working fluid, state change, something like this. So already starts expanding. Okay, already starts expanding. So this depends on the design somehow, constant pressure, heat emission. Okay, expand. So this will be little bigger, like this. Then after that, this starts expanding. Starts expanding through the turbine. Of course, high energy even leaving with bigger volumes. Okay, high energy with bigger volumes. So I just put it here. Yes, bigger volumes. So 3. I think your side, you already outlined this. I'm slow because I have to do this. Okay. This is 3. So 1 to 4. Four has much bigger volume. So here the surrounding connectivity. So how it's connected from 4 to 1, of course, through the surrounding. Releasing fresh air, sorry, releasing not fresh air, that combusted air to atmosphere and instead intake, here there is an intake of fresh air. So this makes, as I explained in very first way, this is a difficult part to understand. So this release energy. This is your Q out. Okay. This is your Q out. And your W compression and W expansion. W compression from 1 to 2. W expansion from 3 to 4 takes place. So during the expansion, pressure reduce, volume increase continues. It's like this. So compression, volume reduces, pressure increase, of course temperature increases as well. Like that. So let me draw that. Yes. It's okay. Good. Yeah. Yes. So this can be the PV diagram, pressure moving. Of course, when you have this understanding, you can look into this TS diagram as well, but anyway, we will understand this first. So it is quite easier because you don't need separate theory-like things. You can just draw this if you understand what's taken place there. Okay? So let me look into gas turbine cycles. You can see that of images. See. So I will copy this maybe. See. It is the same. Yes. No big things. Means you can explain this. This explanation is very important. It's see, they use the word exhaust. Even we used here the word exhaust. Somewhere we have used. So that's how it is. So this concept building of gas turbine cycle, this one is very important. See the dash line, because this is open type, but there is a cycle. Understanding this, you need great practical sense. Of course, you can write equations, no issues, but this dotted line, of course, completes this. Okay, quite easy, quite easy. Once you know the phenomena behind this, the next is going for analysis. That is not a big deal. So like this. Take this. No difference. Ours is more colorful. Yeah, that's also 1, 2, 3, 4, 1. That's it. Okay. So let me add this photo also to make this complete. Quite interesting. So when you understand this story, okay, which means this is quite internalized, especially the connectivity with the sound. So that's it. Okay. Even later we can have TS diagrams as well. So don't worry, we will do that later. PV diagram basically we can understand quite easy. So gas power cycles, you can see change. Oh. Thank you. Yes. So this is the one, all in one. Okay. No difference. It is very important, not about drawing this cycle, but explaining how this is drawn. That is very important. Okay? Because there are practical aspects behind this. So you feel turbine construction is very heavy and feel difficult, but if you think in elemental levels, turbine-like engine designs, we can manage better than the piston cylinder engines when it comes to construction. You can go for low speed ones, not that high speed ones. You can go for low speed ones. It's quite interesting. But we are not trying. Maybe one day, you know that the Sri Lanka Electrical and Mechanical Engineers Sri Lanka Army, they have developed some vehicles. I have seen even in the YouTubes, some armed vehicles. I believe they have a chance because they have all the resources. So if we give this idea, sure they will develop. A turbine, they can try. They can try because they have the resources. They have resources for R&D. Maybe even we can ask them to try this, developing turbines. Not for flying, but for the local stationary solutions. Why not? There may be possibilities. Medium temperature applications, not that very high applications, but medium temperature applications, there may be possibilities because easy to manufacture. As I it's easy to manufacture. Interesting. Yeah. So we always think of construction, Once you know something, how to make this. Okay, that is very important. How to make this? Are there any simple means to construct this? Never think it's not possible, no such thing. Possible, how to make it possible? We have to think about this. Quite interesting. Quite interesting. So, we have started from the most difficult one. So we have done it. Okay. Later we will do the analysis, don't worry. Cycle analysis we will do after understanding this. Same way. Of the cycles, of gas turbine, if we think of engines, okay, maybe this IC engines, we can have some other cycles as well. Okay, we can have some other cycles as well. Give me a second. Give me a second. You know about petrol engines. Okay, you know about petrol engines. Also, you know about diesel engines. Okay, so petrol engines consider, yeah, the technology is about, okay, not like in the gas turbine engines, gasoline or petrol engines. Those are by means of spark ignition. Okay, because There are reasons for that. Okay, there are reasons for that. Mainly for the reliability point of view, this gasoline, the gasoline, this combustion characteristics and all. So the best way may be looking into spark emissions. But for diesel, the combustion can be more controlled. So compression ignition is a possibility. Okay, compression ignition is a possibility. Here also the same way. Intake air you take. Okay. So, exhaust. So you can see same suction, compression. You deliver power and finally you sweeps the combusted products out from this engine. So you have a little bigger volume. Okay, because more energies. So what happens is, it is quite interesting. Connectivity with the surround. You have E in, E out, air in, air out. So let me try to put this from the gas engine. I will get those. E in, air in. E out, air out. Quite interesting. So you have the surrounding. So you have Q out to the surrounding. See how interesting. It's the same if you look into energy balance. See. It's the same. Okay, it's the same. Very good. Okay. So unlike turbine, so this is a different mechanism. So there can be other work interactions as well. So later we will put those back. This is common for the diesel engine as well. Okay. So let me put this for the same. Nicely fit. Okay. So where is Q in here? Where is Q in? Q in. So I will take this. Combustion by ignition. Sorry, compression here. This is compression. So, Q in. You have Q in. here. Okay. Here. Okay. Combustion by ignition. Compression. Okay. Combustion by compression. Q. Quite interesting. That's why always the machine came first and later theory comes. Okay. Same here also. So later maybe the cycles came. Combustion by ignition for petrol. So you all know better than me about this. I'm not going to explain this, but you can see different W components. Okay, different W components. W in intake, compression W in, exhaust another W. Okay, only power stroke you know W. So here it is different. You have many W because of these 4 strokes, only one power stroke. Yeah. Anyway, here this needs to run. Okay, this needs to run. So you can say this. Okay. So same way. You know this very well. W in compression. W out power stroke. W in exhaust. Okay. And then your net out is, okay, your net out is W out minus all the W is. Okay. W out net means power stroke minus all the work it was. Sum of all. Okay. All W. So you will get W out. Don't worry about this. Okay. So there is a way of getting this in easy way calculations. Okay. So that's how it is. So here it's very nice to see this connectivity with the surround. See, with the surround. Quite nice. Okay. Quite nice. So I need to add little more details. We have 30 minutes to go. For gasoline engines, so you have this connectivity. So intake stroke. So piston moves down and this whole gas or air comes. Compression means piston moves. So piston has its own limitations of movement. What do you know about this? You know about this. So this intake volume becomes squeezed. After that, it's ignited. Here you can see the rates down. With that, that is Q in. Okay, so that is Q in. Okay. So with this Q in, that makes this energized and the piston moves down. Okay, looking for lower energy levels. That is the natural way. Always working for it. This is looking for more stable conditions. So the power stroke taken. After that, this combusted gas sweeps out. Okay, sweeps out. It's quite interesting. Okay, sweeps out. Quite interesting. So here, this compression work, this is the strategy: suction, compression, power, and discharge. So for optimal or for the maximum output, compression should have minimum work in. So you have isentropic compression. Maximum work out, you have to have isentropic expansion. Okay. Later we will learn about this isentropic. I think we have learned a bit about this. So no heat leaks, no friction losses. Okay, that is frictionless and only the work done out of this available thing. Of course, you have Q in, but you have Q out as well. Q out is this. This connectivity is Q out. Interesting. Okay. Very nice. Similar way for the compression. Ignitions, we can have the same. Okay, we can have the same. For compression. No need for you to explain much. You know about this. So let me add Q out again. You have Q. This is Q. Okay, this is Q. So same, you can see work inputs and work out and the piston. Okay. So later we will learn about this evaluations, but basically you know this is taken place. So this is the surrounding. So this cycle completes through the surrounding. Okay, this cycle completes through the surrounding. And then for this gasoline engine, the same here in the previous slide. So we think of this spark ignition, energizing at constant volume heat addition. That is here. Okay, that is here. For gasoline engines. Okay, and of course, expansion takes place. Okay, expansion takes place. So your compression, constant volume heat, expansion. And here, at this point, I'm certain, exhaust valve opens, end of the power stroke means this connects with the surrounding connectivity. That's why immediately pressure drops. Fresh air comes in. So there is a connectivity, and through that there is a heat out. So Q in, heat in, Q out, heat out. You can have energy balance. Okay. So by right, so this is the one, the cycle. Okay, you have the compression, you have the energy additions, you have the power, you have the energy release, and ready to start the new cycle, and cycle continues. But when it comes to these 4 strokes, so your intake and exhaust, you can see at low pressures, your exhaust is here. After pressure drops, okay, sweeping the cylinder by means of moving the piston, volume becomes the minimum. Okay, sweeping the cylinder, and then again intake to the fullest by moving the piston to the other end. So fill the cylinder. So this intake and exhaust has different PV additions. For standard air using of this gasoline engines, so you have separate this kind of additions. Okay, separate this kind of additions. It is interesting, but anyway, this is the case. So then you can say addition of this extra for intake and exhaust. Okay, so you may have that kind of, this may be an actual case. So you have compression, energizing power, and then exhaust and intake. So you may have this kind of extra two processes in this cycle. Okay, so this is again intake and exhaust the pressures. You may have different, but this is schematic only. Okay, so this is schematic only. So this is quite okay, and in the same way, so let me take this out at the moment. The same way, this is for the gasoline. If you think of the similar one for diesels, okay, diesel engine, okay, similar one for the diesel engine. Here, left, this is for the gasoline, PV. Same way here, you can see after intake, you have the compression, constant pressure, heat addition, then your power stroke. Power stroke may have two components because when the volume increases during heat addition means the crank turns. That's why. So power is delivered even during this energy addition time. Okay, so high power. That's why diesel engines have more power. Okay, but high pressure, so this needs some robust designs. Yeah, so robust designs. So you need very stable fuel for this, less volatile. That's why diesel is less volatile compared to gasoline or petrol. So the cycles tells everything. So at this point, exhaust open. Okay. To what? To atmosphere. This is the connectivity. So here intake closed, but just before closing, it's open to the surrounding. So this connectivity through the surrounding makes this heat out. So end of the power stroke, beginning of the compression. Force is so strong. Q out, so you can have this cycle. Okay. If we are using air with this four processes: suction, compression, combustion, power, and exhaust, you may have this, but in a basic cycle, only it is this much. So anyway, I will keep this part as well. Okay, Bhutana? So this is quite easy. So your efficiency terms are here. W unit by heat. What is W unit? You know this. Okay. So there is a way of calculating W unit. We will do that in the analysis. So gasoline cycle constant volume and diesel cycles constant pressure, heat addition. So let me take this gasoline cycle out because this is for compression equation. I believe you as the B2 batch with more experience, okay, you can understand this. Okay, and then this gasoline cycle related. There is a theoretical standard cycle, we call it, and not this one, right? Not this one. Give a second, Peter. So let me look into that. Good. So this is the theoretical. Okay. So constant volume cycle or Otto cycle. This left side, we have this, what you have developed, right side. Left side, you have this. You can see constant volume heat addition in the same way. Constant volume heat rejection, same way. So W power, W out is here. W compression or W is here. So this is connected with this engine mechanism, constant volume heat addition. So this is constant volume cycle. Okay. This is the constant volume cycle. So later we will do the analysis for sure. Same way for the diesel fuel, we have another one because that is compression ignition for diesel fuels. So compression ignition, same way you can have the diesel cycle. The name is diesel cycle itself. So this is what we have developed. Okay. So left is the diesel cycle, right is the something when we use air as the working fluid. So we have to replace the air in each and every cycle. So we have suction and exhaust, intake and exhaust. Two more processes here as two straws extra. So this is the diesel cycle. Okay. You know this, and this one I will pass you the video, and also maybe I will pass you the notes for you to go through this. This is the diesel cycle. Okay. Same way I will add another one. There can be a combination of this. Okay. There can be a combination of this. Combine compression and energy additions constant volume and energy additions at constant pressure. Okay. So then the power stroke can finally, you can say, again, there is a connectivity with atmosphere. Okay. So let me add one more slide there. This. So exhaust valve open, here the intake valve, the connectivity is with the surrounding. So this is something like energizing the working fluid initially by means of ignition at constant volume, and then again, yes, initially from the spark, then constant pressure. Okay, so this is constant pressure because of the compression ignition. So two ways of energy additions. So dual means we have two combined. Okay, two combined. So dual cycle. So this is the connection with the ambient, connectivity with the surroundings. So Q out is because of this. Okay. So if we add one more dual cycle for this, it's a similar slide. You can say this dual cycle. So later we will look into TS diagrams, don't worry. So process 1 to 2, compression, isentropic compression. Okay. Later we will study what this compression is. 2 to 3, energizing constant volume. 3 to 4, constant pressure energizing. 4 to 5 is the expansion. Even 3 to 4, there is an expansion. Okay, 4 to 5 is adiabatic. 3 to 4 expansion is because of heat additions. So 5 to 1 connectivity through the surrounding. Okay, good. So that's how is it. So if we take this as a summary, we have all the 8 students are here. Yes. These are answered. How to increase the thermal energy content? Okay, in this working fluids. Yeah. Constant volume heat additions related to Otto cycle, constant pressure heat addition. This is constant pressure cycle or diesel cycle. Combined one is the dual cycle. The engines facilitates this heat addition into working fluid and later deliver a mechanical work. That's why we have discussed IC engines for gasoline and diesel, and also we have discussed turbine engines as well. Okay, turbine engines as well. So basically today this is the coverage. So any more questions? Let me put the final slide. In gas power cycles, how to energize air, that is working fluid. Working fluid. Yes. Thermodynamic system heat addition. How to increase the thermal energy contents. So those are the engines and turbine connected with gas, so air is the working fluid. Generally, air is the working fluid. Energized air delivers the mechanical. So these are the basically today discussion. And here we have understand dual cycle, then diesel cycle. Okay. and then stocks. Yes, diesel cycle and this. What happens? Otto cycle. Okay, so this is for the gasoline cycle. So in the Otto cycle, you see only 1, 2, 3, 4. We have a little extra intake and exhaust also. So once you add this, we call this AR standard Otto cycle. For diesel cycle, when we add that intake and exhaust, it seems like AR standard. Okay, diesel cycles. Later we will discuss those here because of animations. This is not. Finally, okay. So, this all the questions are answered. So that's all today. It's 3:28, so our time is 3:30. We have to stop. So any comments, any questions, any of your engineering problems to discuss? Did you get any new knowledge? Did you receive any new knowledge? Ruben, anything new? Paris, as usual, you are here. Thank you, Buddha.
Yes, sir.
Okay, very good. Understanding is one thing, and I believe this connectivity with surrounding may be new to you. Is that so? Maybe new, not to say new, but that is something we generally neglected. That's why. So cycle always has a connectivity with surrounding when it comes to gas power. Yeah. Each and every cycle once repeats. Of course, the same quantity of working fluid operates through, but it's replenished, means sweeps out and takes in, sweeps out combusted one and takes in the fresh working fluid, fresh air. Seems very simple, but it's very interesting if you can understand this is something like a story, because technology, if you are relying on only maths, you have issues. So let me explain why you have issues if you're relying only on maths. So I will add just one slide. Okay, and I will justify. This slide. This may be the last slide. Eh? So wonderful. This design should be, yeah. One way it is science, blend of science, technology, engineering. There is a huge art behind this profiles and all. Don't expect these profiles they have done with all the extensive calculations. No. Aerodynamics, these profiles, mostly with the people's experience, those are carefully and artistically crafted. And calculations are there. So in a great solutions like this, only with technology it is not possible, because this should not fail in the air and should run for years and years with no failures. Of course, you have to have preventive maintenance. That is one thing. So science, technology, engineering, arts, and maths. Only science, you cannot build this. Only technology, you cannot build this. Only engineering, you cannot create this. And without art, even the balance 4, if you have, this may not be a solution. Even combustion, there are unexplained sciences coming under arts, maybe just experience based. That's why the best engines and turbines are yet to come. So I'm highlighting here technology. So you can see maths as only 1 out of 5. Okay. So if you think 1 out of 5, the maths as the technology, equations as the technology, I think it's a big mistake. Okay. But even without maths, if you can have the front 4, upfront 4, yes, it has some issues, but anyway, it may be better than having just only maths. Yeah. So you have to have all in balance. Okay. All in balance. So what I'm saying is technology is not maths, but technology needs maths. So into technology, as I mentioned, that when it comes to techno-philosophical approaches, it's a blend of everything. Okay, it's a blend of everything. It's a blend of everything. This machine, this looks like more beautiful than a very nicely done decorated cake. Cake ekකට වැඩි ලස්සනයි. So beautiful, so shiny. See the art behind this. See how presentable. Of course, aerodynamics, this aircraft components, of course, they have to be that smooth as well to minimize the drag and all, but see how beautiful, how wonderful. So marvelous creations, and just not because of maths they did this, but they have a lot of hidden reasons related to technology. That is not maths. I'm not undermining maths, but if you have any difficulties in maths, okay, don't discourage that because of maths complications you have difficulties in technology, no such thing. Okay, so better recognize the importance of technology. That's all, Bhutan. Okay, so it's 3:34. Any more questions? This is a wonderful slide. So that's all. So take care, all of you. I can share these slides. Yes. So next week we will do some analysis, and remember, gas power cycle is the last topic of the syllabus. Now we have to do some sample questions, model questions, and we have to, starting next week, we are going to get ready for the exams. Very important. Okay, very important. So I believe all of you can join. Thanks, Butaladin. Bye for now. Well, so any questions before ending? Okay, very good. Thank you very much. Okay.
Will we do model paper or share questions?
Yes, of course, we will do model papers, questions and answers and all. And we have to make sure that you should know thermodynamics. We have to make sure, I have to confirm it, that you should know thermodynamics. Yeah, it is not about the question paper, but I have to assure that your thermodynamics knowledge is there at acceptable levels. I think last slide tells that. Last slide means this one. This tells that. Okay, this tells that. So we are testing the true knowledge of thermodynamics and related technologies, and there can be maths as well. Questions will be very classy but not difficult. Okay. So don't worry about the exam. We will have a very quality question paper expecting quality answers, because these question papers one day the new students will be looking into this, so they have to see the standard. Okay, Vidana? That's all. So we will do model questions, answers, everything, don't worry. So starting next week, even I will post you some questions for you to do. And these are to confirm that your knowledge is complete. Okay, these are to confirm that your knowledge is complete. And I can remember I gave you the gas laws only one session, PV equals in RT, and about little about real, the dealing with real gases. So this one remind me, we have to look into a bit on this. Okay, gas laws, that's all. All the others we are done. Gas laws, even we spend one session. You may have a video for that. So we will try to understand even techno-philosophically how these gas laws are working in real world applications. So that's all, Bhutala. Somehow we are on track. So hopefully in 2 to 3 weeks time, we can wind up, okay, the sessions in a good style, okay, in style. Good. So any more questions before stopping? Okay then. See you. Take care, all of you. Bye, Bhutala. Bye.
Thank you, sir.